Thanks, Nick. Great. Yeah, thanks, Nick, for the kind words. TensorFlow has been really, very big team effort. There are lots of people at Google who've, really built it from the ground up over the last few years. But also over the last year, there's been tons of contributions from the community. The community has helped come together to help not just adopt it to use it, but also to help make it better. And I'll talk about some of that. So before I get into TensorFlow, how many of you have seen these logos before? Do you want to just quickly raise your hands? So a lot of you here, I guess. So these are, all different kinds of Google products, which, you've probably used at different times. The interesting thing is they all use deep learning behind them in one way or another. And in fact, they all use TensorFlow today in some sense, some ways as well. So let's go a little bit more. So, we're talking about machine learning here. And a lot of you are probably doing machine learning yourself or building some of these systems that work there. So let's just quickly go over the complexity. What are we trying to do when we are building a machine learning system, right? There's lots of complexity. I'm going to try to see how we look at those. So let's start with deep learning. This is a very simple neural net, just a few layers, connect all of them together. Of course, the most simplest kind of thing, right? This is how it used to be maybe 20, 30, 40 years ago. And in fact, there's some nets that look like this even today. But more commonly, this is what neural nets look like today. So this is actually last year's Inception network that was state-of-the-art year and a half ago. Now, the newer networks are probably even more complex, even more bigger, 100, 200 layers, and lots more complexity. So how do you deal with this, right? There's so much going on. But it's not just that, right? That's not the only thing that adds complexity. So let's sort of walk through what are we doing when we train this net. I'm going to focus a little bit on training right now, not just the production, inference, or predictions part. So here, you have a network. You basically, how do you train it? You basically do a prediction, see what's coming out, and then you add a loss to it. So you have some targets while training. You have some inputs coming in. You're doing a prediction computation, the targets that compute the loss, compute and update, and then update the parameters based on that. And you sort of iterate over this a few times, the few being maybe hundreds of thousands, millions of times. And eventually you get a model that's trained that you can use. So, of course, in most cases, it's not just one example that you go through. You use a mini batch, and that's just to make things more efficient because our computers today are great at vector instructions rather than just single examples at a time. So that's the first thing you add. The next one, as you start to scale up, you want to distribute things a little bit. So you typically, one of the most common ways is to have this notion of a parameter server. And so you take the parameters and the updates and move it off to a different server. So let's just separate this off into its own block. Now, let's just abstract away that first part that we had over here, where we have the prediction and the loss, and that's basically our model. And that's what's running on typically what we call a worker. And this is a very simple diagram with one machine doing the modeling and another one having the parameters. Of course, that's not where you stop. If you can afford to have, if you have lots and lots of data, you want to parallelize a little bit more. So what do you do then? You put many more workers in there. And so you have all these different models, each running in its own worker, talking to this common parameter server. And there are many ways this is done. The most common way we started doing this a few years ago was asynchronous SGD, and that's very common these days. But you could also do this synchronously, where each of these model workers are basically getting inputs from the input batch, and then sending updates to the parameters servers, and they synchronize things. And of course, while doing all of this, you want to parallelize the inputs. So you're really, each of these workers is independently getting its own inputs. You're not synchronizing in one place necessarily. And if you can distribute this, so it's not just one server holding all the parameters, but maybe many shards of that. And if you have 1 million parameters, maybe you have 4 servers that are holding that. In some cases, many, many more as well. So it starts to be fairly complex, and there's complexity in all of these pieces. In addition, it doesn't just stop there, right? You have servers, and you want to run it on many kinds of servers. So you want to run on CPUs, which is, of course, something we've been doing for a very long time. One of our earliest results was running on something like 16,000 cores across a fleet of servers. More recently, there's been work on GPUs, which work really well and are able to speed these things up. So that's great, and we want to use them. But there's also TPUs, which is our own efforts to make custom chips to actually speed this up even more. People today talk about deep learning, and most researchers and people are saying, we have a lot of compute, sure, GPUs are great, CPUs are great. Give us 1,000x more, we can still do better, right? There's still lots of room for improvement. So there's more and more coming. And we want to make sure the code that we write, we don't have to write the same thing many times. You just write it once, you build your model, and it can run on any of these platforms. But it doesn't just stop there. Once you have a trained model, you likely want to run it in different places as well. For example, on the phones. For example, one of the apps I was talking about there is translation. And in that, you can point the phone at some sign in a different language, and it'll just convert it on the fly right there into your language. And that can't just happen in the cloud. It has to happen on the phone for it to have the right latency for you. So it's really important for us to support those things. It doesn't stop there as well. You have this whole fleet of IoT devices coming up, and there's more and more interest to put things right there at the edge. Because again, you can't really send back everything to the cloud every time. Maybe because you don't have a connection all the time. Maybe because the data is just too much. So how do you actually push these models, push this intelligence to really the edge, to the devices that are there? So supporting platforms like Raspberry Pi, which is, of course, a great hobbyist thing, but there are also more newer chips, et cetera, that work really, really well in these systems. So if you look at all these together, there's lots of complexity in these machine learning systems. It comes from the heterogeneity of the devices that you want to run it. It comes from the distributed nature, especially on the training side, where you want to run it across many, many different machines. And it also comes from the modeling complexity. The models are getting ever more complex. So how do we deal with that? So that's where TensorFlow comes in. We've tried to build this tool so we can address a lot of that complexity, so it's easier for the users not to have to deal with that. That's where the power of TensorFlow really comes. And that's what I'm going to talk about today. So first, just a few things about TensorFlow. As Nick mentioned, it was released just about a year ago. In fact, 2 days ago, we celebrated a full year of releasing it publicly. It's been the #1 repo for machine learning on GitHub over that year. Lots and lots of users. Here are some early stats. And it's not just users and adoption. There's 1 million plus binary downloads, plus people, of course, get the Git repo and really build things themselves. But there's also been a lot of churn and lots happening there. So we've had over 10,000 commits over the last year. That's more than 30 changes a day that are happening to make it better. There's tons and tons of work going on, not just by us, but by the community overall. So we have nearly 500 contributors now, of which more than half are outside Google. Google still is doing a lot of the new code is still coming from Google, but there's tons and tons of contributors who are slowly adding up. For example, recently there was a Windows port that was contributed by Microsoft. There's support by companies like NVIDIA and Intel to make it run faster on those platforms, and many other smaller companies contributing different kinds of things. It's also very popular in universities. There are many courses that utilize TensorFlow for machine learning there to make it easy to run their things. And then here's just a small sample of the companies that are using this today. Lots of big names there, of course, but again, there's a long tail of many small companies that are using this as well. So that's great for the big companies. Let me talk about one example where somebody was able to just pick up TensorFlow out there and use it. So this story is about the guy at the back is really this embedded engineer whose parents are cucumber farmers in Japan, and he was they have tons of cucumbers. One of the things they do is sort all of those cucumbers into 9 different classes based on the size, shape, etc. And this used to be a manual work that his mom used to do all the time. So he decided, this is not something we want to continue. How do we continue to scale that up? And he basically took a lot of pictures. So let's go to this one. So he took a lot of pictures of these cucumbers and sorted it. They've already sorted it, and then trained a TensorFlow model, connected it to run it on Raspberry Pi, connected it to a couple of robotic arms or whatever, just to push them and sort them in the right buckets. And he's able to put this together just by himself with very little code, very little knowledge. And that, I think, is the power of a tool like TensorFlow, which allows not just the big companies and the small companies, but also people to solve real problems that they see. And there's this huge opportunity for folks who are really ready to get their hands dirty and do new things with it as well. So now let's talk a little bit about how do we really address the complexities that we were talking about. Let's start with the heterogeneous part, which is how do we make it portable across all of these things. So it runs, I'd shown a lot of these pictures earlier. It runs today on all of these platforms on Linux, Mac, and Windows in terms of operating systems, on the phones and the Raspberry Pi. A key thing there for us has been to abstract away the underlying devices so it's easy to plug in more, and I'll just show you a picture of that later. When we started from the ground up, we knew that we wanted to run it on many different kinds of platforms. So we really built this core platform in the middle in C++ with it being very easy to plug in different kinds of devices out there. And on the front end, to make it easy for using it from different kinds of things. Python is still the most common language that people use it from. It's more the best supported, I guess, even today. But there's additional support for a lot of these languages today at varying degrees. But you could easily, C++ is something we use a lot for our production needs for inference. For training, Python is still the most common. And then you can use it from Java, Go, Haskell, whatever is the production platform or your language of choice, you should be able to do that. The idea is our core will all be in C++ with a very thin C API on top. And then all of these languages are just very thin wrappers that can be generated for a lot of those things. So it's easy to add support for new languages as well. So here's the rough architecture at a high level. There's the core execution system with the languages on top. And below, if you're familiar with TensorFlow, it has this notion of operations. And what those operations let you do is define things like, okay, add, matrix, multiply, the standard linear algebra kind of things, but also many more that you can write yourself. And then there's a separate abstraction for having custom kernels for each of those devices. Of course, in some cases, you can just recompile the same kernel for different targets, but in some cases, maybe you need a customized thing because you want something much more performant. So if you have a custom chip, or some new company, say, Movidius was building a custom chip, they could take TensorFlow and write a custom kernel that targets their device to optimize it for their chip as well. So in this case, the Python front end is basically where the bindings are in the compound ops, and the ops and kernels I just talked about already. There's also a growing ecosystem of things that people use today in production, like Mesos and Kubernetes for the distribution, and this makes it easier to do those. And then, again, Spark and Hadoop. So integration with all of those to make it easier for these to work well. Let's talk about the distributed stuff now. So one of the things that we were talking about earlier is, as one of the main reasons machine learning has come up is compute. In the last 5 years, a lot of these ideas have been there for a long time. Of course, algorithms continue to improve. But over the last few years, yes, there's been more data, but there's also been tons more compute, both because we've been able to distribute things or because the processors have been getting better, and this is a great place to be. And so we want the system to take advantage of all those different kinds of things. And there are many kinds of parallelism that TensorFlow supports, mostly out of the box, so you don't have to think about it. And so, like in this case, each of the operations that you use in TensorFlow automatically comes parallelized on these platforms. So whether it's CPU or GPU, it'll use as many threads as it has, as many cores as you have. So again, it's trying to utilize whatever's there. There's also, TensorFlow is based on these data flow graphs. So a lot of these models look like graphs with these operations and edges. And it takes advantage of if you have multiple nodes in the graph that can run in parallel, like in this case, these two matrix multiply nodes are completely independent of each other. it can actually parallelize them automatically. It can schedule them if you have the resources to do that. You could, of course, run them on different machines as well. Data parallelism is something I referred to earlier as well, which is now you have these many workers which are basically reading inputs independently and working with the same set of parameters. And again, that's something that TensorFlow takes care of for you. And then the last one is model parallelism. Again, kind of like task parallelism, where you have, let's say, a really large operation. You can split it across 2 different operations instead of 1, and then map it to different machines or different devices, say different GPUs in a machine, and run that way. So lots of different ways of parallelism in there. Again, most of them just work for you. You don't have to think about them. But if you want the control, there's a lot of control in there to optimize things for what you want. So let's just go a little bit about the distribution across devices and how does it work in there. So here's a very simple example of a graph in TensorFlow with some inputs, in this case the bias and the learning rate as parameters or constants. And then the compute in this case is happening on the GPU, whereas the parameters are on the CPU itself. So what happens here is you map the graph, and again, this is something that can be taken care of easily, where all the compute's happening on GPU. So what do we do next? Now you have this graph that's split across 2 devices. There's a lot of communication happening across the edges. So what we do is when the graph comes in, is we break that up across, any edge that's going across devices is broken up, and on the send side, a new node is introduced called the send, and a receive on the other side. This allows us to abstract different kinds of networking stuff. For example, on a single device, like in this case with a CPU and GPU, you might use just the custom, say, NVIDIA's call for moving things back and forth. Whereas if it's across a machine, then you might use say, some RPC thing like gRPC to do that, or maybe even RDMA if that's what your network supports. And then you do this across all of the edges. So after this, the dotted line is really just the notion that receive's going to pull things from the send. And once this is done, though, each device has a full graph that's completely independent of the other devices. And now you can do scheduling completely independently again. You don't have to worry about what's going on in these other places. So this allows us to keep the scheduler itself on each device very, very simple, but still scale things very well across many, many machines and devices. So this has allowed us to scale things across many machines or GPUs. In this particular case, we scaled across 100 machines. It's using synchronous SGD, so we get a 56x speed up over 100 machines in this case. Now let's talk a little bit about the modeling complexity that we were referring to. So these models are becoming more and more complex as we go along. And how can we simplify that part as well? So here's a simple graph again. In this case, what we're really trying to do is typically what a fully connected layer does. You have a matrix multiply with some inputs. You add the weights and the biases, do a matrix multiply, add the bias, and then maybe apply some nonlinearity, in this case a rectified linear unit. So you can, of course, write it this way with full control over exactly what you're doing. You create a variable first for the bias, another one for the weight, and then compute the output that you need to do. Of course, in this case, what you see in that box is something that you want to do very often. It's a very common thing. So instead of having to write all of this yourself, you can basically just use one line of code to build that. And the idea here is to build higher level libraries to have more and more layers that people are used to, but underneath still have the same flexibility that you want from, if you're trying to do research where you want to try something else, maybe with a different nonlinearity or maybe with no biases or some other thing, you can still continue to do that. So starting to add higher level abstractions to help with some of these things. And so in this case, if we go back to this particular graph, it ends up that, sure, this is a fairly complex graph, but each of those blocks in there, which is, layer or more layers, and each box is just one line of code, right? It's much more manageable this way rather than having, a crazy number of lines of code starting from the really basic stuff. And it's allowed us to do much more complex things research in new kinds of models and build ever larger growing set of models as well. So we have a lot of different algorithms in there now, lots of them pre-specified for you. Again, you're not limited to that, but you can use them yourself directly, the standard linear classifier regression, DNNs, and some combination of those. The DNN linear combined is actually interesting because you can combine if you are used to doing large-scale logistic regression, you can actually now combine that with deep models as well and use different tricks for what makes sense for you. But also some more standard models like SVM or k-means, et cetera, you can do those too. So, very simple machine learning. Again, you have your feature columns, you build your linear classifier, and then you just call fit on your data, just as you might with, say, a framework like scikit-learn, except now you can also run it on GPUs, you can distribute it across many machines and do all the other fancier things as well that you want to do. There's also a lot more tooling provided along with that for the distributed training, for evaluations. There's a graphical interface for debugging and looking at how your metrics are looking over time. And also, in fact, there's support for serving. If you're trying to deploy this to production, there's something called TensorFlow serving that manages your models, manages maybe multiple versions of your models and so on, does batching for you. A lot of things that you might look at for any production use. So, this is the thing that we were talking about earlier with parallelizing all of these things. Well, this is exactly what TensorFlow is here to do for you, so you don't have to worry about all of that. And the whole idea is we have this system that handles the complexity for you, so you can really focus on what you want to do, focus on your problems, your ideas, and how to solve them, not really on the system behind solving this idea. Earlier there have been many different systems in the past that handled part of these problems. We've tried to really put it together because we feel the same problem ourselves. We use the system ourselves to make things really, really good for us. Of course, if you don't want to train models at all, you can use APIs directly. Google Cloud Machine Learning offers a bunch of APIs for vision, speech, translate, etc. Some of you might be familiar with those. And also there's a managed service to train TensorFlow in the cloud, so you don't have to worry about managing VMs and all of that stuff, which is great. So, yeah, there's been lots of cats in deep learning literature, I guess. Starting from our first example back in 2012, where we trained this classifier, or trained this network to generate this cat, basically. Not really generate, but we trained on a lot of YouTube videos, and we realized as we were looking through the neurons, this was all totally unsupervised back then. And we realized that we had a neuron that would learn to identify cats that correlated very strongly with cats. And this was the sort of the rough picture that it would correlate the best with, so that was pretty interesting. But there's some much more interesting stuff with cats more recently, so I'm going to give you one example. So there's this cat, somebody in somebody's garden, and this person was seeing the cat come in every day or every other day and basically make the garden dirty. It would just poop in the garden, etc. So this person's getting really, really annoyed with it. So what does he do? So he has a security camera, takes a whole bunch of pictures of that cat, and then trains a simple classifier based on using TensorFlow to identify the cat, which is great. So what next? Now, sure, you've identified that. What can I do with it? So the next thing he does is he actually attaches it to connects it to his sprinkler system. And so, so whenever the cat comes in, it just turns on the sprinkler system and, there it goes. That's pretty amazing. In this case, it was an NVIDIA engineer, so hooked it up to an NVIDIA chip and doing all of this, which is really fun. Of course, the classifier isn't quite perfect, so sometimes he ends up getting wet too. But this is, I feel that I love this example because this is the kind of fun thing you can do with machine learning. It's really about your ideas, what you want to do with it. Of course, this particular one is something that you would do at home or just making your personal life better. But even at work, there are just so many problems today that can gain from machine learning, and I don't have to teach that to you. I guess all of you here probably are very familiar with that. But there's just tons of potential. We're just getting started, just scratching the surface so far. And I really hope to see machine learning be a part of every single thing that we do. That's why we built TensorFlow, to make it really easy for you for doing all the things you want to do. Thank you.